Okay. Here's another example of a covering space. It's a map from the unit vectors in R4 to the set of rotations of R3, SO3. Remember, that's the orthogonal matrices, 3 by 3 matrices, with determinant 1. And the map is given in that way. It looks kind of random. But it's a wonderful map, and it's an example of a covering space. It turns out, though not obvious whatsoever from this description, that the preimage of any point in the codomain has exactly 2 elements in it. A much more conceptual way of writing down that same map is through what's called quaternions. And you should look this up if you're curious. I won't spend any more time on it than right now. And as quaternions, it's the map from a unit quaternion, which turns out to be just a unit vector in R4, to this map from R3 to R3 that carries a vector in R3, which you can think of as what's called an imaginary quaternion, to this other quaternion, which turns out to be imaginary as well, thereby giving a map from imaginary quaternions to imaginary quaternions. And this map is given by conjugating by the given unit quaternion using what's called quaternionic multiplication. And if you write this out in coordinates, you get this ridiculous expression. So now here's the idea of a covering space. It's a continuous map between 2 topological spaces. And if you think through all the examples we've talked about, or maybe just the ones that you're familiar with already, they have the feature that the preimage of any element in the codomain is not just some random subspace of the domain, but that subspace of the domain, which is the preimage of an element, is in fact discrete. So it's a discrete subspace of the domain. In other words, the subspace topology on the preimage agrees with the discrete topology on that preimage. So that's somewhat remarkable. But better, it is so locally in B in a very certain sense. So I might say this, the second condition as, I'll say, a third shot at the idea, yet better, is that it's locally trivial. So now remember in the previous board an example of a trivial covering space. So it's locally in the topological space B. It looks like this. Projection. So here's now a precise definition of a covering space. Maybe I'll put it up here. So definition, a covering space is, here's the data, a continuous map between topological spaces and of course not any old continuous map, but one that satisfies an articulation of this local triviality, such that for all points in the codomain, the following stuff exists. There exists first an open neighborhood of that point. Next, a set F, and it'll probably depend on B, so I'll put F sub B. Actually, I regret that already. There'll be a set F, which we regard as a topological space with discrete topology. And a homeomorphism. Phi with the pre-image of that open. So that's some subset of E, which is necessarily open because pi is continuous, and not any old homeomorphism, but one such that, and I'll write this in two ways. One is so that if you apply pi to any element of that pre-image, thereby obtaining an element of U, that will agree through this homeomorphism simply with projecting down onto U. So such that this diagram commutes. Alternatively, if you'd rather not think in terms of diagrams, if the homeomorphism goes this way, it's saying that U, for all B prime inside of U, B prime is equal to first apply phi, and then apply, for all B prime in U and little f, or an element capital I, or little I inside of f, little b prime is equal to phi applied to b prime I, and then projected. That's an alternative way of saying that this diagram commutes. So that's the definition of a covering space. It's a continuous map such that for every point in the codomain, there's a little neighborhood about that point whose not just whose preimage is a discrete topological space, in this case being abstracted as F, but also it is that space locally. It depends sort of constantly in the point in the base, in the codomain. Here's some quick terminology. So given a covering space, E is the total space, and B is the base space. Let me draw a picture of one of the examples, and then I'll prove it more rigorously. Remember this example of covering space, given by t goes to e to the 2 pi I t. Drawn a picture like this. So let's see just intuitively that this is an example of a covering space. So let's see. We should check that for every point in the base, such as that point, that there is a little open neighborhood about it. There's our open U about it. and a discrete set. So we'll take f to be the integers z, so that pi inverse of that open, which it'll be this collection of open intervals in the reals, infinitely many of them, countably infinitely many of them. And we're supposed to show that there also exists a homeomorphism between z cross u and that preimage. But I mean, that preimage, if you straighten it out and draw the real line like this, that preimage is a collection of opens that looks just like this. And that's just a copy of u, one for every integer. So this is a heuristic justifying why this map is a covering space.